Good day. This is MEG 224, Engineering Mechanics 2, Dynamics. Lecture 8, Planar Kinetics of Rigid Body, the Principles of Work and Energy. This is the part A of that. And this could be found, it can be found in chapter 18 of Engineering Mechanics, Dynamics by R.C. Hibella. Lecture objective. The objective of this lecture is to develop formulations for the kinetic energy of a body and define the various ways a force and couple do work. Kinetic energy. Work and energy methods will be applied to solve planar motions. Planar motion problem involving force, velocity, and displacement. But first, it is necessary to develop a means of obtaining the body's kinetic energy when the body is subjected to translation, rotation about a fixed axis, or general plane motion. Consider a rigid body shown in the figure, which is represented here by a slab moving in the inertial XY reference plane. This, the inertial XY reference plane. An arbitrary height particle of the body has a mass dm. It's located at a distance r from the arbitrary point p. If at the instance shown, the particle has a velocity v subscript I, then the particle's kinetic energy Ci is half dm mass times vi square. Kinetic energy of the entire body is determined by writing similar expressions for each particle of the body and integrating the result. So T is half integral dm vi square. This equation may also be expressed in terms of velocity of point P. If the body has an angular velocity, omega, then from the figure, we have that Vi is equal to Vp plus Vi with respect to P. And then if we break up this into their components, this is Vpx in the x direction, Vpy in the y direction, and then we know that V of I with respect to P, where we differentiate, our velocity is omega r. So this is omega, and then this is r. So an omega is in the k direction. It's pointing out of the paper here. Then this is r. So this is omega r. And then r is now in the x and y direction of components. So when we collect the like terms, we know that k cross I is j, and then k cross j is minus I. So we now square the magnitude of Vi, that is this, we square, this is the result. So that's Vi dot Vi, which is equal to Vi square, which is this component square plus this component square, the x component square plus the y component square. So that one will now give us this Vpx square. Then we have Vpy square, omega square y square, omega square x square, then 2 Vp omega y, 2 Vp y omega x. So when you collect the like terms, you know that r square is equal to x square plus y square. So this guy here, omega square y square, then plus omega square x square will give us omega square into r square. So that is what gives birth to this. Then we now plug in this into the kinetic energy equation, which gives us this half Vp square integral dm, because this term is actually the V square. So plus this integral y dm. Then this guy is half omega square. Here, all the two are disappearing because of the half in half mv square. Here, half omega square integral r square dm. And this is the moment of inertia of the body about its center of mass. So the first integral on the right represents the entire mass, the m, where you integrate the mass from the beginning to the end. That gives you the entire mass of the body. Then y bar m is equal to integral m y dm. Y bar x bar m is equal to integral x dm. So that is the second and the third integrals locate the body's center of mass with respect to p. So the last integral is the body's moment of inertia, IP, computed about the z-axis passing through point P. Thus, we have half mv square, mvp square, then plus vpx omega y bar m, then plus vp omega x bar m plus half I omega square. So, as a special case, if the point P coincides with the mass center G of the body, then this x bar and y bar will be equal to 0, and therefore t square, t is half mv square plus half I g omega square. Both terms on the right are always positive because vg and then omega are squared. So the first term represents the translational kinetic energy referenced from the mass center, and the second term represents the body's rotational kinetic energy about the mass center. Translation. When a body of mass m is subjected to either rectilinear or curvilinear translation, as shown in this diagram, the kinetic energy due to rotation is 0, since omega is equal to 0. The kinetic energy of the body is therefore T is equal to half mv g square, rotation about a fixed axis. When a body rotates about a fixed axis, passing through point O, this figure, the body has both translational and rotational kinetic energy because it is rotating about a fixed point. So that T is equal to half mv square plus half omega I omega square. The body's kinetic energy may also be formulated by noting that Vg is Rg omega. V is equal to omega R. So that T is equal to half into I plus mr square omega square. By parallel axis theorem, the term inside the parentheses represents the moment of inertia, IO, of the body about an axis perpendicular to the plane of motion and passing through point O. Hence, T is equal to half I naught omega square. From the derivation, this equation will be the same result as earlier equation, since it accounts for both translational and rotational kinetic energies of the body. So general plane motion. When a rigid body is subjected to general plane motion, as shown in this figure, it has an angular velocity and its mass center has a velocity Vg, Therefore, the kinetic energy is C is equal to half mvg squared plus half ig omega squared. This is because it is undergoing rotational as well as translational motion. System of bodies. Because energy is scalar quantity, the total kinetic energy for a system of connected rigid bodies is the sum of the kinetic energies of all its moving parts, the work of a force. Several types of forces are often encountered in planar kinetic problems involving a rigid body. The work of each of these forces has been listed below as summary. Work of a variable force. If an external force acts on a body, the work done by the body, the work done on the body by the force when the body moves along the path S is shown in the figure. So is integral F dr, which is equal to F cos theta ds. Hence, theta is the angle between the tails of the force and the differential displacement. And the work done should be in the direction of the force, or the force and the displacement should be in the same direction. The integration must account for the variation of the force direction and magnitude. Work of a constant force. If an external force Fc acts on a body shown in the figure and maintains a constant magnitude Fc and constant direction theta, while the body undergoes a translation S, the above equation can be integrated so that the work done becomes U for constant force is equal to Fc cos theta times S. S is displacement, and it's not ds again because there's no change. Sorry, the S is constant and the force is constant. So work of a weight. The weight of a body does work only when the body's center of mass undergoes a vertical displacement dy. If this displacement is upward, as shown here, the displacement is upward, then the work is negative since the weight is opposite to the displacement, and that means work UW is minus W delta Y. Likewise, if the displacement is downward, the work becomes positive. In both cases, the elevation changes is considered to be small so that W, which is caused by that gravitation, is constant. Work of a force. If a linear elastic spring, work of a spring force. If a linear elastic spring is attached to a body, the spring force Fs is equal to Ks acting on the body does work when the spring either stretches or compresses from S1 to S2. So in both cases, the work will be negative since the displacement of the body is opposite direction to the force, as shown in the figure. When you pull, the spring has an initial length, and that's in the initial length, they call it unstretched length or unstretched position. When you pull it, and then you now attach load to it, it will pull the body or the particle back. When you push it and you attach load to it, it will push the particle. So the work is US, which is minus half Ks square, Ks2 square minus half Ks1 square. So this is the final position, and then this is the initial position, where S2 is greater than S1. That is the final work done is greater than the initial work done. There are some forces that do no work. These forces, there are some external forces that do no work when the body is displaced. Note, the forces act either at fixed points on the body, or they have a direction perpendicular to their displacement. Example, the reaction at a pin support about which a body rotates, and normal reaction acting on the body that moves along a fixed surface, and the weight of a body when the center of gravity of the body moves in horizontal plane, as shown in the figure. When you have this object, and then this is the center, and then the center of mass is at this center, and then this object moves along this line, and there is no change in the position of the center of mass, then the center of mass, which is the weight, does no work. A frictional force F acting on a round body as it rolls without slipping over a rough surface also do no work. This is because during any instant of time dt, F acts at a point on the body which has zero velocity, that is, stationary center is IC, and so the work done by the force on that point is zero. In other words, the point is not displaced in the direction of the force during this instant. Since F contacts successive points for only an instant, the work of F will be zero. Work of a couple moment. Consider the body in figure A, which is subjected to couple moments. M is equal to FR. If the body undergoes a differential displacement, then the work done by the couple forces can be found to be considering the displacement as a sum of separate translation plus rotation. When the body translates, the work of each force is produced only by the component of displacement along the line of action of the forces, dst. This is the displacement, and this is the force. As shown in B, clearly, the positive work of one force cancels the negative work of the other. When the body undergoes a differential rotation d theta about the arbitrary points, figure C, then each force undergoes a displacement ds theta, which is this is the line. This force acts this way and pulls this to this position, which is the S. And then this force acts this way, this is the S. And then from here to here is R. And therefore, half of it is R over 2. Hence, the total work done is the UM, which is F force times displacement R over 2 d theta plus F R over 2 d theta. So R over 2 plus R over 2 will give you R. F will come out, then d theta. So FR now is M as shown here, which is, so the UM is M d theta. So the work is positive when M and the theta have the same sense of direction, and negative if these vectors are in opposite sense. When the body rotates in the plane through a finite angle theta, measured in radians from theta 1 to theta 2, the work of couple moment is therefore UM is equal to integral theta 1, theta 2, M d theta. If the couple moment has a constant magnitude, then UM is M theta 2 minus theta 1. Thank you. End of part A. Please do not forget to like, to subscribe to my video channel, to share my videos, and press the notification bell for new videos. If you are one of my university undergraduate students, please do not forget to subscribe with your real name. The part B is on the way very soon. Please watch out for it. Thank you and God bless.